Hello everyone, welcome back to our Calculus 2 course. Today in this video clip I will start chapter 8. It's about more applications of integration techniques. We're going to show you one application today on section 8.1. It is about arc length. So the main purpose of this section is to help you how to measure the length of a curve. Okay. So basically the idea is this: say you have a curve, it's a function f of x, right? And say, x-axis right here, y-axis right here, and I want to calculate the arc length run from A to B. This length right here, L, from here to here. Okay? It's the general ideas in calculus. Whenever you want to calculate the whole thing, the idea is to chop it up into small pieces, and we calculate one small piece at a time. Same thing here for the arc length. We chop it up into many little pieces, and we're gonna measure the arc length a little piece at a time, and we add them all up. We have the total arc length. Okay, so let me just try to zoom in. Say you have a curve. Make it a little bit more curvy. Okay? So in the middle. Basically the arc length from here to here is approximated by this little line right here. Let's call it ds. Okay? Oh well, it's supposed to be delta s, okay? And then when we take the limit when n goes to infinity, where n is the number of the little pieces we have, we call it ds. Okay? Just like delta x. And then later we have dx before we chop it up into many little pieces. Alright? And how do we calculate ds in here? We use Pythagorean theorem. This is ds calculated by this is what? Dx right here, dy right there. So ds squared is equal to dx squared plus dy squared. Again, it's supposed to be what? Delta s and then delta x and delta y. When this is far many. But when we take the limit when n go to infinity, I try to explain to you the whole idea is like this. It's very small, it's a little d instead of delta. It's the same thing. Similar. Okay? So this is the main thing that we start with using Pythagorean theorem. Diagonal square is equal to hypotenuse square. It will be equal to the sum of the squares of two sides. Okay? So take square root on both sides, or we can divide both sides first. I can take square root of both sides first. Square root of both sides, we got ds is equal to square root of dx squared plus dy squared. Okay, that is the key. And say I can do it this way. There's two ways to think of the problem. It depends on which variable you are calculating on. So let me rewrite it up here. ds is equal to square root of dx squared plus dy squared. Okay? So, if you integrate in terms of dx, I can think of it this way. ds equal to square root of dx squared, factor it out, 1 plus dy squared over dx squared. I just simply factor dx squared out, so I can rewrite it as square root of 1 plus dy over dx square times dx outside, because dx squared inside the radical is just dx outside. So give us the first formula for calculate the arc length. So the arc length usually we know by n, and for length is equal to the integral x run from a to b square root of 1 plus dy over dx square dx, where dy over dx is just f prime, the function prime. I erase the picture. Let me redraw it right here. So you got a function f of x, right? X run from a to b. So the length L right here is calculated by this formula, where dy over dx is just like y prime, which is fx prime. And I want to start with this one because later on you learn about parametric equation, then you can use this formula in general Right? So x equal to function of t, y is equal to function of t. We're going to go back to that formula later. I think it's in chapter 10 or something later. But I will work show you guys this formula first. So I derive the formula from the original one up there. And of course, when you guys move on to calculus 3, and we may have one more variable, right? A curve in 3D, the x squared, dy squared, dz squared, it works the same way. Okay? What if your curve is not like this? What if your curve is like this? Another word, you guys have a function. This is not y equal to f of x anymore. You have a function like x equal to, say, g of y. Now what? We don't say x run from a to b anymore. This is like y run from c to d. That means instead of dividing both sides by factoring dx out, now we can factor dy out. So instead of factoring dx, I'll do it this way. Square root of dy square, I factored it out, so what? Dx over dy square plus 1, and you do the same way. Okay? You're going to have ds is equal to dx over dy square plus 1 square root, and then times dy outside. So when it's calculated by integral, now the variable is y, the y run from c to d, square root of 1 plus dx over dy square. I just tried to write the book way. If you write this, it's okay. It's the same thing. Times dy. Okay? So same formulas. This applies to this kind of curve where y is a variable and x is a function of y. You just interchange the rows of x and y. You have another formula. So you learn one, you know the other. Right? Now we're going to talk about the last item of this section. It's called the orthogonal function. Okay, so far we have the formula to orthogonal function in terms of x, okay? From a to b, the square root of 1 plus, what? How do we write it? This way, then f prime of x square dx, okay, or f prime of x is the same thing as dy over dx. Oh, I'll just write it this way, it's shorter. It's the same thing. Okay, so this formula helps you to calculate the orthogonal of the curve where x run from a to b. This length that we're talking about. Okay. Now, we want to make this formula a little bit more powerful. Think of it this way. What if I change b to a variable? So fix a, okay? A will never change. A will be right there. If we move b to the left or to the right, then the orthogonal is going to change. Now think of b as a variable. Okay? A is a constant. B is a variable. Okay? So because b is a variable, our book uses x. So I'll write x as a variable. And x is changing. So instead of thinking of taking the integral from a to b, where both a and b are fixed, we think of the integral from a to x, where a is fixed and x is changing. Okay? So whenever you plug in a new value for x, you're going to have a new integral. We're going to have a new orthogonal. So instead of calling L, let's go say Lx then. The orthogonal, that's a function of x. Okay? Now we use x for the upper bound already. So to avoid any confusion with the variable inside the integral, let's change that into t. So this is going to be integral 1 plus f prime of t squared dt. Okay? But t is just a dummy variable. So if in the problem, later on you guys see in the homework, you got like f of x is equal to x squared, then you just simply replace f by t, you got f of t just t squared. And whatever you do with this, right, same thing, f to t squared, so f prime of t is 2t. It's not a big deal, it's just change variable. That's it. And this one right here, we call it the orthogonal function, okay? And you have orthogonal function, say XL equal to a function of x. So whenever you want to calculate the length from A to X, all you have to do is plug in the value for X, and you have a new arc length. It's not fixed anymore, it's a function. Okay, that's the whole idea for 8.1. I think it's good. It's a good time to show you guys some example of how to calculate and some difficulty that you may have in this type of problem. The idea is simple, not hard. The harder part is you have to take care of that radical inside the integral, right? You got the derivative and square and plus 1, and then take square root. And you see what in here? 1 plus something square, right? Usually with this type of problem you have to think of tricks up, and that makes the problem hard. But the idea is very straightforward. So let me give you an example, a couple examples. Let's just start with the first one I see in here. Y is equal to 1 plus 6 times x raised to the 3/2, where x runs from 0 to 1. Okay, nice. Now I have to calculate the arc length of this function when x runs from 0 to 1. Okay, so we just apply the formula. So y is here, y is f, right? So y prime or dy over dx, however you write it, y prime or dy over dx is equal to derivative 1 is 0, the derivative of this is 6 times 3/2 is 9, x to the 1/2. Now you see why they had to set up the function nicely, so that when you square it up, you have a very nice function. So y prime square or dy over dx square is 81x, right? 9 square is 81, x to the 1/2 square, just 81x. Then apply the formula right here. The arc length from 0 to 1 is integral from 0 to 1 square root of 1 plus y prime square, which is 81x, then dx. Now for this problem, I think you guys just need to do it yourself. Let u equal to 1 plus 81x. So du is equal to dx, 81 dx. Okay? So this integral is equal to integral, okay, when x is 0, u is 1, x equal to 0, then u is equal to 1, x equal to 1, then u is 82. I plug x equal to 0, I got 1. Plug x equal to 1, I got 82. So 82 right here, square root of u, so u to the 1/2. And then dx is 1 over 81 du. And I'm glad you guys can do this one easily. Okay, move on. Find another one. The next one is this. $36y squared is equal to x squared minus 4 raised to the 3rd power. X squared minus 4 raised to the 3rd power. And x is between 2 and 3. 2 less than or equal to x, less than or equal to 3. And y is positive. Yeah. Y is non-negative. Oh. So this is the boundary. A is 2 and y is, b is 3. Okay? And they give you y positive, so you can solve for y, you have a function of y, I think. So you don't have two functions plus or minus anymore. So this is what y squared is equal to x squared minus 4 cubed divided by 36. So y is x squared minus 4 raised to the power of 3 over 2, everything over 9. 6, I mean. Take square root on both sides. And you want to calculate, they ask you to calculate the arc length of this curve where x runs from 2 to 3, y is positive. Okay? And do the same thing. Y squared, derivative y first, and then square it up. See what you got? So y prime is 3/2 divided by 6. 3/2 divided by 6 is 3 over 12, so a quarter. of x squared minus 4 raised to the 1/2, and then times 2x. I'm using the chain rule in here. The derivative, right? You bring 3/2 outside, times 1/6, so 3/12, which is 1/4, and then x squared minus 4 raised to the power of 3/2 minus 1, which is 1/2, and then chain rule say that we have to multiply by the derivative inside, which is 2x. All right. So y prime square is gonna be this is gonna actually can be simplified a little. So this is 1/2, right? So 1/2 x times x squared minus 4 raised to the 1/2. So y prime square is 1/4 x squared times square root of x squared minus 4. Oh, no more square root because squared it up. Oh, no more square root. That's better. Okay. So we plug into the formula. The arc length is calculated by integral from a to b, square root of 1 plus f prime square dx. F prime or y prime is the same thing. So this is equal to integral from 2 to 3, square root of 1 plus 1/4 of x squared times x squared minus 4 dx. Okay. Let's try to simplify that thing a little, see if it helps. This is square root of 1 plus 1/4 x to the 4 minus 1/4 times 4 is just 1, so I don't have to write 1 in here, of x squared dx. Integral from a to b now is 2 to 3. Alright, so how did you take care of this problem? Well, actually this is a perfect square as you see it, so it requires some algebra, right? So integral from 2 to 3. 1/4 x to the 4 minus x squared plus 1 is really 1/2 x squared minus 1, everything squared. Alright, you can factor this out, it's going to be equal to this. And then dx, is that right? 1/2 is 1/4, and then 2 times of x minus, and then 1, yeah, that's right. So this is integral from 2 to 3 of 1/2 x squared minus 1 dx, and I will let you go from here. You will be able to calculate. So as you see that the hardest part for this problem is what? How to convert from here to here. You have to see the perfect square out of it. All right. You can think of factors. All I can tell you right now is because I've been working with this type of problems a lot. So I just when I see this equation or this function, I automatically see this is perfect square. It takes time to practice. Okay? You can think of substitution. You can think of other way, but think of this perfect square is going to work. So let me try another one. This thing involving what sine or cosine, a trig function. See how it goes. I just choose problem from the book. Okay. Y equal to ln of cosine of x. X run from 0 to pi over 3. This would be a positive function, right? Okay? And calculate the arc length of that thing. So we still have to calculate y prime. Y prime. The derivative ln is 1 over. So 1 over cosine of x. The derivative of cosine is negative sine x. Alright? So y prime square is, what's it? This is negative tangent, I think. Right? Sine over cosine is tangent, negative tangent. Y prime is tangent square of x. Alright, so that's very nice. The length is calculated integral from 0 to pi over 3 square root of 1 plus y prime square, so 1 plus tangent square of x. You see, it's very nice, right? dx. And 1 plus tangent square is secant squared, I think, integral 0 to pi over 3 secant squared with square root with secant of x dx, and I think that we have a formula for secant that I gave you before. The integral of secant of x is ln of secant x plus tangent x. I think you can check. I'll spread it from 0 to pi over 3. I'll let you do the rest. Okay. So anyway, whenever you have a problem, just look on the formula and use all or some or many of those integration techniques you have before to calculate the answer. Okay. I claim that in reality, usually this formula is very hard to find the exact answer. So in the worst case, if you're unable to find the exact solution, then the book gonna ask you to do approximation. Right? We have the midpoint rules, the trapezoid rule, the Simpson rules, those kind of rules, and maybe many more. You can apply the rules to calculate the arc length. Okay, so the height of our section right here. So I only cover one section today, so it's gonna be pretty short. Its length is equal to integral from a to b square root of 1 plus f prime of x squared dx. Okay. Alright, arc length function integral from a to f, and then square root of 1 plus f prime. Now it's not x anymore because we use x for the upper bound already, so we change it to t. Okay. How about let me show you one more example using the arc length function. Let me look in the book, see if they have any arc length function. Okay. Okay. I'm trying to look for an example in the book on the exercise, but they only gave us one, so let me just use that one. I'll learn a function. Okay, we have the function f of x is equal to. Actually, any problem on the arc length function is going to work, so just choose any example. F of x equal to. Just use the same example we had before. Easy one. 1 plus 6x to the 3/2. Okay? Now, we want to find the arc length function. So, what do? Arc length function is integral from, you start from what? Actually from 0. Okay? X is greater than or equal to 0. Right? Integral from 0 to x. Okay, going up. Square root of 1 plus f prime t squared dt. Okay, this is just the initial point. Say, this is x. This is 0. X is moving. The first point is right there. Kind of like that. Okay. I just make it up because I don't see where it's like. It says start from 0. Let's start from 1. Doesn't matter. Let's make it start from 1 then. 1. 1. So 1 is right here. Okay. So we want to calculate the arc length, start from 1 and move all the way to the right. We could be start from 0, I just make it up that number. Okay? So it's the same thing here. So instead of doing it with f of x, we can change it to f of t, 1 plus 6t to the 3/2. So f prime of t is derivative 1 is 0. This is 9t to the 1/2. So f prime of t squared is 81t. Okay. So pretty much the problems say the same, and you see the difference at the end. Okay. Apply the formula right here for the arc length function. This is integral from 1 to x, square root of 1 plus f prime t squared is, this is square, I forgot that, is what, 81t dt. You do the same u sub, let u equal to 81t, right? Then du is equal to 81 dt, and then you have to change the boundary to, when t equal to 1, then u is 81, t equal to x, then u is 81x, right? It's 1. Oh, u equal to 1.